Good afternoon, ladies and gentlemen. I would like to welcome you to our presentation at the ACI Spring Convention about the latest development of ATENA regarding the modeling of fresh concrete and the simulation modeling of 3D concrete printing. So in my talk, I will cover the main features and show some examples of these two areas of the latest development in ATENA. So first of all, let's talk a little bit about ATENA. ATENA is a software for verification of structural capacity or crack width. It contains some unique features which I think you cannot see in other simulation softwares. So for instance, as you can see on the right side of our window, this is at the bottom, this is exactly the screen that you see when the program is running. So immediately as the program is calculating, you see how the structure deforms, how the crack develops, how the reinforcement is yielding cracking. You can follow, you can define some monitoring points and follow, for instance, in this case, the load displacement curve. Well, another unique feature is the very realistic and user-friendly interface and also realistic display of crack widths which you can see on the surface of the structure of our reinforced concrete structures, or you can see it also inside the structure. Among the new things that we have introduced now in the version 2025, this is the support of transport analysis in our new preprocessor. Before, this was only available in our ATENA Science version. Now it is available also in ATENA Engineering. With this transport module, you can simulate fresh concrete or fire modeling. Another new things, new improvements is the possibility of Python scripting and support for 3D modeling and simulation. I will come to that later on. So now let's talk first about the modeling of fresh concrete in this transport module. The transport module supports, you activate it in the project settings in the new 2025 preprocessor, and the transport module supports both thermal analysis as well as moisture analysis, and you can also make a coupled transport moisture analysis. Well, I will focus a little bit more on the feature in the transport analysis for modeling of fresh concrete. That means hydration, development of thermal heat during hydration of concrete. So for that, we basically this shows the dialogues that you have available now in the new ATENA software for the definition of the concrete. So you really can define the composition of the concrete material, and it is using a representative element volume based on which the macroscopic characteristics of the material are derived. So based on the composition of the material, filler density, aggregate density, and so on, the material parameters are defined, and the hydration curve is generated either based on an analytical model, or it is also possible to define it from some user data. That means if you have the test data, how the hydration heat develops in your material, you can directly include that into the software. Now let's have a look at one example. So this is a hydration of a massive concrete abutment, and the idea is to simulate the heat development. So here you see the animation of this heat development. You see the temperature reaches about up to 60 degrees. And why this is done? This is done because often on the construction site, the investor requires the construction company to check that the heat inside, or the temperatures inside this massive concrete block, remains below certain limits, and also typically the gradient needs to be checked. So in this case, which comes from a real consulting projects, Various parametric studies have been analyzed to check the highest temperature. In this case, you can see the limit was 70 degrees Celsius, and another limit was that the difference between the maximal temperature inside and the temperature on the surfaces of the structure should be below 20 degrees. So with the software you can easily see how these thermal hydration temperatures during the hydration process will develop, and you can also verify what will happen if you use different cement types like cement 1 or cement 2. Or you can also play with boundary conditions, that means the insulation of the outer surfaces and so on. So this is a very nice tool. And what you can also do, that it is possible to combine or import the thermal fields into the stress analysis, or even into the taking into account creep and shrinkage. And you can simulate how, for instance, in this case, this shows how the cracks will develop, not only on the surface of the structure. These figures, they show the crack width on the surface of the structure. This is the two figures show the crack width on the surface, and here at the bottom we can see the cracks in the interior of the structure. Very interesting visualization is also this one at the at the bottom left, which shows how the cracks develop inside of our massive concrete abutment. Now, the next topic I want to cover is the very new and interesting development that we continuously for the last about 5 years are developing. That is the simulation modeling of 3D concrete printing. So in this case, of course, the important feature is to demonstrate the process of the gradual buildup of the structure. In this case, this is defined by specifying a path or printing path, which then along this printing path, then the individual finite elements are activated, their self-weight is gradually introduced, and possibly also, for instance, the shrinkage. Another interesting possibility is that we can also drive this printing process by the G-code. G-code is actually the data format that is being used by the printing machines. This is the standard format in the industry. And this G-code is then used to activate the finite elements along the printing path. In addition, as you can see here on the right, it is possible to directly build the model directly from the G-code. So there are actually two ways how we can build the finite element model to run the simulation of 3D printing. One is that we develop the model in CAD, mesh it by finite elements, and then we activate these finite elements by the G-code. Or another possibility is that we don't need to have a CAD data file for the final configuration. We can directly build it up based on this G-code, which contains basically the coordinates of the moving of the printing head. And of course, important part is the modeling of the hardening of the fresh concrete. So for that, we have two possibilities. Either we provide directly the time-dependent parameters for the materials, for our material model, or we can generate them based on the hydration curve, which is maybe the most suitable and easiest approach. So based on this hydration curve, we have a relationship how to relate the hydration degree of hydration to the compressive strength, and then based from the compressive strength, we generate all the necessary material parameters for our concrete model, which our concrete model is a fracture plastic material model, which can capture the cracking in tension as well as the crushing or failing of the material in compression. So now let's have a look at some examples. So first we will show an example which demonstrates a collapse of a simple cylinder. which has been tested in at this publication at the bottom, and we confirm nicely that the collapse occurred at the height of about 30 centimeters. Here you see the shape of the structure at the point of collapse. Now the next interesting experiment, also from laboratory, is the evaluation of the strength of such a 3D printed structure. So in this case we will be modeling, we will be simulating the printing process, then we will let the structure rest for 28 days, and then we will load it up to failure. It is interesting to note that in this case we are modeling each layer, and also between the layers of the printed concrete we are introducing interface elements. In this case these green surfaces also represent interface elements between these ribs that we can see here in this model. Here you see an overview of material parameters and also the data for the interface properties we took from this publication. So this is just an overview of this simulation scenario. So first there is a printing of the structure in about 35 minutes. Then we let the structure rest for up to 28 days, and then we load it up to failure. In this resting phase, the material Young's modulus and the strength of the material further develops, and of course shrinkage is also developing throughout the model. So this is here you see some stages from this printing process, and here you see some eccentricity that which develops in these in these walls, in these longer parts of the specimen, and which is up to about 5 millimeters. This also shows the differential strains plotted in the model for shrinkage. And here we see a simulation of this printing process. Here you see the development of this initial eccentricity. And now, after the maturing time, we start loading the specimen up to failure. So this is again just the repetition of this process, and then loading by the vertical force up to failure. So this on the next slide you will see a very good match between the calculated, which is the green line, and the experiment, which is the red line. It is interesting to note that this dashed blue line represents the model strength that we would obtain if we just load it without the simulation of this printing process, without the development of these eccentricities. And here you see the final failure pattern, which I think very nicely corresponds to what has been observed in the real experiment, where the failure was observed in these longer segments of these vertical walls. Now a little bit bigger example. So we are moving from small example to a bigger one. So this is a 3D printed small building which has been printed or constructed in Czech Republic about 3 years ago. Let me just show here a short video from the development of this building. It was called protozoan because it has shape of that animal. And here you see the printing of this building in the laboratory, where it was also tested up to failure. This shows the testing process, and this was also simulated in our software ATENA. And here you see some basic ideas of this model, because it contained these vertical small columns which were filled with concrete and also reinforcement. So let me go to some results of the simulation. So you see in this case, the model was developed directly from the G-code. So we didn't start from the CAD model, but we used directly the G-code, which was driving the printing machine to also drive our simulation. Here you see the animation from this modeling process for the simulation of the 3D printing. This shows also the development of plastic strains, and you can nicely see that the areas where the printing head needed longer time before it came to the same position in the subsequent layer, so that these areas with the red, they have a lower plastic strain developing, but the green areas where the printing head, because these walls are shorter, so the printing head came to the same position again sooner than in these bottom and top parts. So that's where we see that a little bit higher plastic strains have developed. And it is interesting to note also that we have some higher plasticity also at this top opening, because there is much more deformation, inelastic deformation. And also we can see some cracking at this top part due to this printing process, but the printing was successful. But in the next example, we are showing a hypothetical situation if on the right we would be printing with 10 times faster printing speed, and then we see a collapse of the wall. So this shows how this process or this simulation of printing can be used to verify the stability of the structure during the printing. So with this, I would like to conclude my presentation. So ATENA is, in our opinion, very unique tool for checking or verifying your structures, or reinforced concrete structures. And the latest development now in ATENA 2025 is also the support in the engineering version for thermal analysis, modeling of fresh concrete. And our latest new development is also for the modeling and simulation of this new technology of 3D printing. So with this, I would like to thank you for your attention. I would like to remind you that we are here at the ACI convention at the exhibition hall. You can find us at the booth number 604. And also you can follow us on our website as well as on the social media. So thank you very much, and looking forward to meet you in person at our exhibition booth. So thank you and goodbye.
ATENA program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.